So as you've been working through book one of the daily workout, you'll see there's plenty of space in here for you to write your answers in. And also towards the back, you'll also find many answers that you can just do a quick mark of your work. Now these just have the values, but they don't explain actually how to get that answer. So what I have now are my work solutions. And in this video, I'm going to be talking through the worked solutions for July. So the first question, 1st of July, question number 1. I gave you a little bit of help here. So we have a right angled triangle, and I always find it really useful if we know that this angle is theta, just to identify the hypotenuse, which is the longest side, the side adjacent to the angle, and also the opposite side. And then again, this is really down to you how you use these answers, but it's your work, so you can add as many notes as you want to them. So what I did was just write down SOHCAHTOA. Sine theta equals opposite over hypotenuse, and we're trying to find the value of theta. So I just rearranged this to say that sine to the -1 of the opposite over the hypotenuse is going to be equal to our angle of theta. And even though some of these questions later on they might seem quite straightforward, it's always a good idea to put down all of the equations you're using, to rearrange it, and then put in your working. So this is just equal to 8 divided by 10. And that's then 53.1. And I gave my answer to 3 significant figures because we had 3 significant figures in the raw data over here. Now the next one, when we talk about a proportionality relationship, we're really talking about what's the link between kinetic energy and mass. Okay, and here I put non-relativistic because ultimately towards the end of A-level you might start looking at how mass can actually change as objects get closer to the speed of light. But we're going to ignore that. We're just going to think of our normal everyday objects. And I'm just going to use the equation that says the kinetic energy equals a half mv squared. You know that from GCSE. And therefore, if you've got something where we have the same velocity, the kinetic energy is going to be proportional to the mass. Heavier objects, if you double the mass, you're going to double the kinetic energy stored. And then the next one here, we just did a quick calculation for kinetic energy and momentum. For this one, I just wrote down the values that I identified in the question. And I've got the 2 equations. So P equals mv, where P represents momentum. And then kinetic energy is a half mv squared. So again, simply writing down the equation, putting in the numbers and giving the answer. Now you could have called this 540 kilojoules. You could have said 5.4 times 10 to the 5 joules, but I just gave it as 540,000 joules. And again, for momentum, just times the numbers together, 36,000 kilogram meters per second. And again, you'll notice when it comes to A-level, although at GCSE we might have used a slash, at A-level we use this kind of superscript up here. So seconds to the -1 means per second. Okay, and that's something which is probably one of the biggest changes you'll first see as you start doing these A-level questions. Okay, 2nd of July. So much like the first, I've got my triangle here. We know that the angle theta is 40 degrees. I've identified the adjacent, hypotenuse and the opposite side, and I've put down the data from the question. The adjacent side is 2.8 meters, and we're trying to find the hypotenuse. So again, writing down SOHCAHTOA, we know A, we know theta, but we don't know H, and therefore I'm going to rearrange this to make H the subject. I've put the numbers in, and so here the answer is 3.7 meters. What's the relationship between resultant force and acceleration? Well, basically, when you have a bigger force, you have a greater acceleration, and the 2 things are proportional to one another. And again, this symbol here with just 3 dots just means therefore. Okay, and again, you'll see a lot of stuff that you might recognise from GCSE maths. It's going to be coming up all the time in A-level physics. And then a bit of GCSE, explain what a vector quantity is. Some of you might remember this from Despicable Me. So a vector quantity has magnitude and direction. So it's got a size and also the direction in which it acts. And of these quantities over here, speed isn't a vector, mass isn't a vector, and neither is energy. And these are kind of simple, easy mark questions that you might get given. And again, this isn't really much beyond what you might have seen beforehand. For the 3rd of July, a bit of Pythagoras. Now, you've probably known this for a long time, but this comes up all the time. There are so many right-angled triangles, especially when you're doing the mechanics topics in A-level. And I've just said that A squared plus B squared is equal to C squared. Again, if there's anything that you're not sure about, you can always look back at my GCSE Physics Online website, where I do have videos where I explain that, and I also show how this area plus that area is equal to that area, in Lego, of course. Right, the relationship then between frequency and time period. We use a capital T for time period, and that might be one wave cycle, or maybe at A level we might even think about the time period of something which is moving in a circular path. So capital T is our time period, and therefore the frequency is proportional to 1 over t. The next one, just a very simple calculation, but we want to know the frequency. So I've started with my equation that says V equals F lambda. I've rearranged it to say that the frequency is equal to the wave speed divided by the wavelength. I've put in the numbers and it gives this number here. Now, this number here, is it 2 significant figures or 3? Well, at A level, the rule tends to be that if you have a trailing 0, that adds to the significance. So 330 is 3 significant figures. 3,300 would be 4 significant figures. Now, really, the way to get over any doubts you might have, the best way to actually represent this would be standard form. So a better way to represent this number here might be 3.30 times 10 to the 2 meters per second. And we can see now by using standard form, we can actually see that that 0 adds to the significance. But for the questions in this book, if you can see 3 figures, that's going to be 3 significant figures. And that's why I've rounded up this answer here to 127 hertz. So that one there, your standard, staple, simple, I suppose, GCSE equation where you're just putting in the numbers. But it's going to get a lot more tricky. You're going to get really good at that by the time we get to the end of this book. Okay, the 4th of July. Now, if there are any words in the questions that you're not quite sure about, you can just Google it. So this one here just means we have a right-angled triangle. And we want to calculate the length of the hypotenuse when the sides are 3.3 and 4.0 centimetres. So again, this is just a squared plus b squared equals c squared. I've rearranged it, and therefore the hypotenuse, the length of that longest side, is equal to 5.2. And for the units for this, I've given it as the same units given in the question here. Again, it's completely fine if you were to say 0.052 metres, they're the same answer. What's the link between acceleration and mass for a constant net force? Sometimes we talk about the resultant force, sometimes we use the word net force, depending which textbook you're reading, the video that you're watching, or even the exam board that you might be studying. So here, we can say that A is equal to F over m, and for the same force, the acceleration is inversely proportional to the mass. If you have something which is heavier, for the same force, there's going to be less acceleration. Then we're going to calculate the current. Just using Q equals IT. Q is the charge, I is the current. I've rearranged it, put the numbers in, and we've got an answer with the units to 2 significant figures. Nice and straightforward. 5th of July, again, we have another right-angled triangle. I want you, by the time you start your A-level course, or if you're doing your A-level course at the moment, to be really confident with using Pythagoras and a bit of trig with our right-angled triangles. So here, using a bit of Pythagoras, we can rearrange to make x the subject. And I suppose really I should have said here 7.0 squared plus x squared. That means x is equal to 7.1 centimetres. What's the link between momentum and velocity? With momentum, the momentum of an object is proportional to the velocity. And here, I just did a very simple model of the atom. Now, this is something we're going to explore more, especially when we look at things like quantum physics. Now, this is a very simple model where we have our protons and neutrons together in this dense nucleus, and then we have orbiting electrons, which are negative, in shells around it. Now, as we do a little bit more physics, we realise that actually sometimes the electrons, we don't necessarily think of them as particles, but they might have wave-like properties. They can also change the energy level that they're in. And again, this is our very simple model of the nucleus. So this is kind of where we start, but this can explain a lot of the particle physics and nuclear physics we do at A-level. Okay, the 6th of July. Again, a bit more Pythagoras, just label stuff on your diagrams, put the numbers in, and diagrams really, really help. So this one here, because our raw data is to 2 significant figures, I've given x as 13 meters. The link between kinetic energy and velocity is that the kinetic energy is proportional to the velocity squared. And again, depending on which textbook or video or even exam board you're studying, we sometimes use different ways of representing the kinetic energy. Sometimes it's E with a small k, or sometimes it's KE. Both of them are absolutely fine. Your teachers will understand you're working out. The examiners, if they're marking your work in the future, they'll know exactly what you're talking about. Now the next thing, in a DC circuit, so these are our simple circuits we're going to be dealing a lot with at A-level. We have a cell here, and the longer side is the positive and the shorter side is negative. Now conventional current goes from positive to negative, but in an electric circuit it's the electrons, which are these small negative particles, which are moving around, and the electrons are going to be repelled from the negative end and attracted towards the positive end. So the electrons go this way, but conventional current goes this way. Now a lot of the time at A-level we're also going to be looking at positive things which are moving. It could be a positron, which is a positive electron, or a flow of protons or even ions, and therefore in those examples the conventional current is going the same way as those particles, but with electrons they go in the other direction to conventional current. 7th of July. Hope your summer is going well if you're watching this on the 7th of July. So standard form, super useful, and all I did here was I wrote down these numbers in standard form. So 8.99 times 10 to the 9. I suppose I really could have added more zeros after this to show that we've got lots of zeros which may have added to the significance, but I just did the numbers that we had here. Now these numbers here, they might become really familiar as time goes on. You might recognise some constants that you're given later on in the course, as well as things like the speed of light, which, although we just normally round it down to 3.00 times 10 to the 8, this is a more accurate version of it. Now the next one, I just wanted you to work out the ratio of two sides. Now again, what you can do is put in the numbers, so maybe the hypotenuse is 14.14, the opposite side was 10.00, and because that's 45, this must also be 45 degrees, and that means A is equal to 10.00. Now the ratio of side O to H is just 10 divided by 14.14, which is 0.707, and that just happens to be the same as sine of 45 as well. Also, the ratio of A to H is equal to 0.707, and that's the same as cos theta. So what this really shows is that sine theta is just the ratio of this side of a triangle to this side, cos theta is just the ratio of this side to this side, and sine 45 is equal to cos 45. Okay, the next one, just using speed equals distance over time, rearrange it, put the numbers in, get the answer, and here that's equal to 960 metres. 8th of July, yet again I wrote these numbers in standard form. We can see because these numbers are really small, there's a negative number up here, and also we can see that the reason we use standard form all the time is because otherwise we'd have far too many zeros in all of our working out. So these one over here, again, these are constants that you're going to be coming across all the time in A-level physics, especially the mass of an electron. Now normally we use a value to three significant figures of 9.11 times 10 to the minus 31 kilograms. But you will be given this in your data and formula book, but you will also be using it multiple times over the next couple of years, and it's just something which you're just going to remember. Now for this triangle over here, we've got the opposite, the hypotenuse, and in order to work out the adjacent side, you need to work that out yourself using a bit of trigonometry. Because if we know that this angle is equal to 30.0, we know that this side is equal to this side is equal to 2.20 and that side is equal to 4.40. We can use a bit of trig to work out the value of A. And when we do this, again, just like on yesterday's question on the 7th, the opposite over the hypotenuse is sine theta. The adjacent over the hypotenuse also happens to be equal to cos theta. Okay, the next one, I'm going to use the wave equation that says the wave speed equals frequency times wavelength, put in the numbers, and this gives the value of 3.0 times 10 to the 8, which is the answer that we'd be expecting because we're calculating the speed of light, in this case of red light. Sometimes as well, you might see an equation that says c is equal to f lambda. Sometimes we use the letter c to represent the speed of light, and some exam boards, including AQA, often use c just to represent the speed of a wave. Again, it's all the same physics, but there are slightly different ways of showing that. Okay, the 9th of July. Now normally, when we talk about electrons, we say that electrons are negative and they have a charge of -1. A neutron is 0 and a proton is +1. But these are actually the relative charges, and if we were to measure the charge in coulombs, we'd actually find that electrons have a charge of -1.60 times 10 to the -19 coulombs, and protons have a charge of +1.6 times 10 to the -19 coulombs. And the size of this charge here is what we call the elementary charge, which is E. Okay, again, stuff like this you're not expected to know, but you can find it with a quick Google, or I suppose other search engines may be available, but you can just Google it and you can find out a lot of the data that you need. Now, rearranging equations are it's just something you just have to know about. Now, I think that formula triangles are really bad. They get you lazy, and it means that students don't really understand how we're actually rearranging things. And often at A-level we have many more than just 3 terms in our formulas. So, first of all, I wrote it out, and then I did the same things to both sides. So first of all, I took AT away from both sides to say that V minus AT equals U, and then I just swapped the two sides over to say that U equals V minus AT. That's all I did. We could also, I suppose, actually rearrange this if you wanted to make A the subject, to say that A is equal to V minus U over T, and therefore that's our change in velocity divided by the time taken, which gives us our acceleration. And again, I've given this answer to 3 significant figures like our raw data, and the units are meters per second squared. You will always have a calculator at A-level, but sometimes it's still good to understand the process for how you multiply these numbers together. So for this one over here, effectively what I did was multiply this number 2 by this number, which is 4, and then we've got 10 to the 4 multiplied by 10 to the 7, so I added 4 and 7 to make 10 to the 11. So that's why the answer for this is just 8 times 10 to the 11. And again, it doesn't matter which order you do it in. So now we've got 4 times 2 times 10 to the 11, 3 times 3 times 10 to the 11. And this one over here I calculated as 12 times 10 to the 11. But when we give answers in standard form, best practice is that this first number here should be between 1 and 10, or just under 10. So it should only have 2 digits, like this with a dot in the middle, and therefore 1.2 times 10 to the 12 times 10 to the 11 is 1.2 times 10 to the 12. Again, this one over here, I wrote down the equation. I performed the same to both sides, so v squared minus 2as equals u squared. I just flipped them over to put u on the left, and then I took the square root of all of this. So u is equal to v squared minus 2as. Now the next one over here, we want to know the final velocity. We know it starts at rest and has uniform acceleration over a certain distance. Now what you can do is maybe just select the equation, and again this is one that you will have seen at GCSE. It's not often used, but it's used all the time at A-level. Something which I think is actually really useful is if you write down S, U, V, A and T, we can start to fill these headings in with what we see in the question. So the displacement S is 20 kilometers, so that's 20 times 10 to the 3 meters, and I'm going to convert into our standard SI units. It starts at rest, so U is 0 meters per second. We don't know our final velocity, but we know the acceleration is 0.80 meters per second squared. And for this one, we're not given the time, but we don't need it because we've got S, U and A, and we can use that to find V. Now these types of questions about motion are SUVAT equations. You may have seen some of these in GCSE maths. You will definitely see these in A-level maths, and you'll definitely see a lot of them in A-level physics. So my advice is always write down SUVAT, maybe vertically down the side, fill in the data with what's given to you in the question, and then you can select the right equation. And this equation here doesn't have a t term in it. So all I did was I rearranged it, I put the numbers in, and it gave me an answer, which I then gave as 180 meters per second, which is to two significant figures. Again, strictly speaking, I could have put 1.8 times 10 to the 2 meters per second, and that then shows in standard form that this answer is definitely to two significant figures, not necessarily three. Now again, that's maybe me being a little bit pedantic, but it's good to get into good habits from the start, and that means that as you do more work in class, you might have a look at some assessments, or even potentially something like Isaac Physics. It is important to use an appropriate number of significant figures for your final answers. Right, the 11th of July. Just like last time, 4 divided by 2, well, I'm just going to put that as 4.0 divided by 2.0 multiplied by 10 to the 4 times 10 to the 7. So that's 4 plus 7, which is 11. And then 4 divided by 2 is just 2 times 10. Oh, sorry, I've made a mistake there, haven't I? It's not 4 add 7, it's 4 take away 7. So 4 take away 7, and that's going to be equal to minus 3. So 2 times 10 to the minus 3, which is the answer I've got down here. The next one, I did the same thing again, and I got an answer of 0.50 times 10 to the minus 3, which in proper standard form is 5.0 times 10 to the minus 4. This one over here, because we've got 10 to the 7 divided by 10 to the 7, that's just 2 divided by 4, which is a half. And now we've got 2 divided by 4, which is 0.5. And then we've got 7 minus 4, which is 3. So that's 5.0 times 10 to the 2. Now again, I'm going to give you lots of practice at rearranging equations. A lot of these are going to be used all the time throughout A-level. Some of them might not come up until year 13. So this one over here is looking at the electric field strength between parallel plates. Now you don't need to know that, but you just need to look at these symbols and think, okay, how can we make D the subject? I'm going to multiply both sides by D, divide by E, to say that D is equal to V over E. Here, this one is actually to do with the way that light behaves, and we've got the wavelength of light, we've got a diffraction grating, but again, you don't need to know the physics just yet, but I'm using these equations so you become more familiar with them as you go through the course. Now this, I think, is one of my favourite equations that not enough people use. Now the area of a circle is equal to pi r squared, and the radius is equal to d over 2. So the radius is half the diameter. Now if we substitute this into here, effectively what we can say is that the area of a circle is equal to pi times the diameter squared divided by 4. And that's because if r is d over 2, r squared is equal to d squared over 2 squared, which is 4. Now the reason this is useful is because a lot of the time you might have to make a real measurement of something, potentially maybe like the diameter of this pen here, and you don't measure the radius, you measure the diameter using maybe a caliper or a micrometer, and often d is the measurement which is given. Now you could just take that value of d and divide it by 2, but it's better, I feel, just to use this equation that the area of a circle equals pi d squared over 4, and here I've rearranged d to be 4a over pi square rooted. Now the next one, we've got an object which slows down from 70 to rest in 5 minutes. Again, we could think about adding in suvat here, and I think if you do that, it then shows clearly that if it ends up at rest, the final velocity is 0 meters per second, but its initial velocity is equal to 70 meters per second. The time is 5 minutes, and again, we always give our times in our standard SI units of seconds. 5 times 60 is just 300 seconds, and we want to calculate the acceleration. So although you might not have used this approach at GCSE, you might still have used the same equations, and here, because it's v minus u, it's going to be 0 minus 70, and that's going to give us our negative acceleration. So that's really important. Acceleration, just like velocity, is a vector quantity, and therefore values can be positive or negative. 12th of July, let's keep those calculators away. Now, first of all, 2 and 4 is 6, and these ones here are both times 10 to the 4, so that was a fairly straightforward one. What I'd say that for the next one, though, is you might want to think about, you could always write this as 2.0 times 10 to the 5 plus 0.40 times 10 to the 5. Okay, and what I've done there is I've made both of these raised to the same power, and then it's clear to see that 2 plus 0.4 is going to be equal to 2.4 times 10 to the 5. Similarly, you can do a similar method for this one, so that's 4.2 times 10 to the 5, and 8 plus 4 is equal to 4.8 times 10 to the 5. Okay, some more questions here. This one we were looking at the charge. Now you might look at the charge on maybe an individual particle moving in a magnetic field. Again, this is the kind of thing you might be doing in year 13 when you're looking at magnetic and electric fields. So here Q is the momentum P over BR. We then have V equals W over Q and F equals BQV. Again, just rearranging to make Q the subject like that. Now for this one, I've used two equations here. First of all, I've just used one equation, which I've rearranged, put the numbers in to give 71.4. Okay, and this one here is 7.00 times 10 to the 2 hertz. Well, that's just the same as 700. So we can see by giving something in standard form, it's very clear to see how many significant figures that raw data has been given to. So you should hopefully by now be used to using this wave speed calculation. Again, waves is going to be one of the topics that you might begin with, or you'll definitely be doing in year 12. Now, just as before, we've got 2 times 10 to the 4 minus 4 times 10 to the 4. These are both 10 to the 4, so it's 2 minus 4, which is minus 2. The second one is 1.6 times 10 to the 5, and again, similar methods will get you these answers over here. Now, Newton's first law, you will know about this from GCSE. What we say is for Newton's first law, it's a law about the forces acting on one object or one body, and here there's going to be no resultant force. So there might be a force F1 here and F2 here, but if they are equal in size but acting in different directions, there's going to be no resultant force, and that means if the object is at rest, it's going to stay at rest, and if it's moving, it's going to continue moving at a constant velocity. So real examples could include maybe something like this ruler over here. It's at rest on the table because there's no resultant force acting on it. If you've got something moving, it maybe is a bird moving at a constant height, at a constant speed in the same direction. It could be a car going along the motorway at a constant speed. Loads of examples you could maybe think about and choose from. Now this one over here. The reason that this book is a physical book and not just a thing which you can only do as a digital download or see on an e-reader is because I want you to be drawing stuff in with a pencil and a ruler. Now, I didn't use a pencil for this because of the way I put the answers in on the iPad, but what you need is a real pencil. I'd suggest a 30 centimetre clear ruler, and that means you can actually get a nice long straight line. You also need your protractor when it comes to measuring angles. And what you want to do is maybe for this one here, work out the scale. Now on this one here, so the 14th of July, and the first thing we're going to be looking at are the mean, mode and median, 3 different sorts of averages. Now, to be completely honest, we tend not to use the mode and the median in A-level physics. We tend just to use the mean. So you simply add all the numbers together, divide by 7 to get an answer of 5. And then I think, by ordering the numbers like this, it's clear to see which ones come up most commonly and also which one is the middle value. Now, Newton's second law, F equals ma, is very much a special case that we tend to use at GCSE. However, sometimes we have a mass which changes or a non-constant acceleration, and a better definition of Newton's second law is that the force is proportional to the rate of change of momentum. And this is where we look at the forces acting on one object, but now we have a net force or a resultant force. A resultant force is going to cause the object to accelerate. Now, number 3, we looked at using the parallelogram method, and that's a scale drawing. Now, This is why you need to have two protractors, because if you're going to use a ruler and you want to get a line parallel to this, you can sort of judge it something a bit like this, but a better way to get a parallel line is to have two protractors, and what you can then do is as you move them along, we can then get our parallel line like this. And that means that you can adjust it depending on the size of the gap. So again, if I line this one up with that, we can see this is where we get our parallel line. And where the two cross over is where we put in our resultant force. Now we just want to know the magnitude, so its size. And again, using your ruler, you can work out the scale, as in how many centimetres is representing 3.2 newtons. And again, we can see that this big arrow is about twice the length of that smaller one. So it gives us the idea that about 5.8 newtons is an appropriate answer. So this one over here, we tend not to do too much of this at A level, but it's still a skill that you need to have and the ability to do your own scale drawing. Right, the 15th of July. Again, we've got some different numbers, and all I did was I crossed them out as I put them in numerical order. I used this to calculate the mean, which is 45.1. I suppose, strictly speaking, we could also say that this is equal to 45 to two significant figures, like our raw data. But then the mode and the median are also both 45. That's both the most common value and the middle value. Now, Newton's third law. We're going to cover a lot more of this going into year 12. We're looking at forces. But basically, this is about the forces between two different objects. And the force of object A on object B is equal and opposite to the force of object B on object A. And these forces are the same size, they're the same type, but they act in opposite directions. So Newton's third law is about the interaction between two different objects. Using a graphical method, once again, this is very much, although it doesn't look like it, it's actually just another parallelogram. So we want to be drawing our lines, perhaps again using our two set squares. We can adjust them, and what we find is where these cross over is where we draw this in here. And we can see that 1 centimetre is about, or 1 centimetre is equal to 1 newton. If you measure the length of this, it's about 10.5 centimetres, and therefore 10.5 newtons. Right, go on to the 16th of July. These numbers in standard form to three significant figures. We've got 6.63 times 10 to the minus 34. You're going to cover a lot of this when we're looking at quantum physics and the behaviour of maybe things like electrons and how that interacts with the surface of a metal potentially, or even the energy of a photon. So that's Planck's constant. 1.66 times 10 to the minus 27 is actually the atomic mass unit, and that's the average mass of protons and neutrons. And then 8.85 times 10 to the minus 12 is something which comes up in year 13 when we're looking at the permittivity of free space, especially when it comes to electric fields. Now, a car's travelling at a constant velocity of 30 metres per second, so we can maybe think about Newton's first law, where there's no net force, so something moves at a constant velocity. The forces acting on it, well, the driving force from the engine is going to be equal to the drag and the friction, and the weight acting down is equal to the normal contact force of the road pushing back up on that vehicle. Now, for this one, we're going to be using a mathematical method. So it doesn't really look like it, but this problem actually is a triangle problem. We can see what we have here is a right angle triangle. We know we want to find out the angle theta. We've got the value of the hypotenuse that we can work out. We know the adjacent side to this angle, and the opposite side is the same as 6.0 newtons. So I labelled this on my diagram, the hypotenuse, the opposite, and the adjacent. That then allowed me to work out the angle by using tan theta equals opposite over adjacent to get 37 degrees. And in terms of working out the hypotenuse, I just used Pythagoras. So just 6 squared plus 8 squared is equal to 10 squared. And again, we might recognise this as a 3, 4, 5 triangle. But again, that's why these skills are important. That's why at the start of July I had loads of questions just looking at right angled triangles. The 17th of July, again, we're just looking at converting these numbers, which are incredibly small, into standard form. The numbers actually do mean something. We've got the mass of a proton, a mass of a neutron. We've got Boltzmann's constant, which comes up when we're looking at gas and pressure, and also big G. This is to do with the gravitational field strength, and this, again, is going to be something you come up and sort of see all the time when you're in year 13 looking at gravitational fields. Now, we then want to look at some alpha, beta, and gamma radiation. Now, beta minus is our standard negative electron. We also look at beta plus at A level, which is a positive electron or a positron. But at GCSE, we just tend to think about the normal standard negative electrons, and that means it's got a charge of -1, whereas an alpha particle, because it's got 2 protons in it, has got a charge of +2. Again, the mass, 2 protons and 2 neutrons, is 4. Beta minus, it's going to be about 2,000th the mass of a proton, so actually 1 over 1,830. And then finally, gamma is not a particle, but it's a wave of energy. Now, the next one, using scale drawing is super important. Again, it's a skill that you need to develop. Keep your diagrams as large as possible and choose a scale that fits with the kind of the data that you've been given in the question. Now, for this one over here, 40 newtons down, 60 newtons across, a nice right angle, and then you can just, using your scale, measure the length of this, and you should find that the force is about 72 at an angle of 56 degrees. Now, you could always check that mathematically using a bit of Pythagoras and a bit of trig, but this one here, again, the idea isn't to get the right answer. I mean, it is, but the idea of this question here is to have you practice using your pencils and rulers when it comes to scale drawing. 18. Calculate the following to an appropriate number of significant figures. Now, again, we always give our answers to the least amount of significant figures in the question. So these ones over here have got 2 significant figures. Those are 3. And although that one's given to 5, this one's only given to 2. So we can only justifiably give our answer as 1.6 times 10 to the 3. This one over here, we've got the equation. We rearrange it to make V the subject. We're going to put the numbers in, and here the basketball is travelling at about 15 meters per second, so a fairly straightforward one. But again, being able to rearrange this into that can be done fairly quickly the more you practice doing your rearrangements. And again, using a mathematical method this time, we're going to be, again, drawing a diagram really helps. And for this one, what we can see is that 950 squared plus 390 squared square rooted gives an answer equal to 1,030 newtons. And we can give that to 3 significant figures, like these have both been given to 3 significant figures as well. 19th of July. Again, simple maths, but again, what this is about is looking at the least number of significant figures in the question. So that's 2, 3, 3, and 2, which is why the answers are like this. And really, this one here, again, we could give it as 1,500 or 1.5 times 10 to the 3 to show that that's actually 2 significant figures and not 4. This one over here, what I always tend to do is the numbers on here I write on the triangle. I've identified the adjacent, opposite, and hypotenuse, and then we're just going to use sine or cos for either the adjacent or opposite side. And the reason I did this is because later on we're going to be resolving a force into its vertical and horizontal components, and therefore it's really important to select either sine or cos where appropriate. Now, if you've got something that emits alpha radiation, because alpha radiation is 2 protons and 2 neutrons, the mass number goes down by 4 and the proton number goes down by 2. When you have beta minus, what actually is happening is that inside a neutron is turning into a proton and ejecting a high-speed electron, and therefore the proton number goes up, but the total amount of nucleons in that nucleus stays the same, so the mass number doesn't change. And gamma radiation, well, it's the particle being emitted. Sorry, it's not a particle being emitted. It's a kind of a little packet of energy, and therefore the proton and mass numbers don't change. On the 20th of July, you should be getting into the hang of this by now. I'd say, again, use this just in your calculator, and you can give your answers either to 2 or even to 4 significant figures. Now, the reason that this question here should make sense is because yesterday you were just looking at the opposite and adjacent sides of a triangle. We've now got something very similar, but what we're looking at is resolving this 100 Newton force into its horizontal and vertical components. So I've just called them FV and FH. And again, I kind of put in my triangle here, and I used a different colour pen. I identified that 100 is the same as the hypotenuse, the opposite is the same as the vertical component of force, and the adjacent is like our horizontal component of force. So using cos for the horizontal component and sine for the vertical component. And again, you might have done this in maths already. You occasionally may have done it in a bit of GCSE physics, but this is just a staple skill, and it might be looking at the horizontal components and vertical components of a force or any other vector quantity, including velocity. Now, this one over here, again, it's a SUVAT question, so you might want to identify these from in the question. We want to know u. We know the final velocity, we know the acceleration, and we know the distance. So we're going to say that v squared equals u squared plus 2as. Rearrange to make u the subject, put the numbers in, and find that initially it was going at 1.3 meters per second. 21st of July. We're going to solve this thing here. So basically, if 4x plus 20 is 0, then 4x is equal to minus 20 and x is minus 5. And again, these symbols here, greater than or less than, are used occasionally in A-level physics. The other thing here I really want to point out is that although the square root of 4 is plus or minus 2, when it comes to A-level physics, we'd normally just say that the square root of 4 is equal to 2. It's often the positive value that we're actually interested in most of the time in A-level physics, not the same in A-level maths. Now this one over here, it's only a small diagram just kind of make you actually do this. But again, we're looking at the vertical and horizontal components of this force at this angle. And here, the horizontal component, because it's this angle given up here, not this one down here, we're going to use sine to work out that that value is 7.81. And the vertical value is a lot bigger, as 22.7. This one over here, we're going to look at the maximum theoretical height that a ball could reach. And what we're saying is that all of that kinetic energy is transferred to potential energy, and there's going to be no losses due to friction or drag with the air. And we're going to be using a value of G of 9.81. Now at GCSE, we tended to use a value of 9.8 or even 10 for our gravitational field strength. At A-level, we're always going to use the value of 9.81, and that's given to you in your data or formula book. So I've just put in these two things here, rearranged to make the change in height the subject, and this gives a change in height, theoretically, of 136 metres. In reality, it would be a lot less than that. On the 22nd of July, we're going to start with a definition. Definitions are easy marks to gain. It's just something that you just need to identify and then learn. So that's what we mean by 1 joule. And if we want to look at the area underneath the velocity time graph, what does this represent? Well, that's going to represent the displacement of that object, and the gradient would be representing the acceleration. So we're going to be doing a lot more motion graphs as we go into A-level. And then the energy transferred per second is the power, because P is equal to E divided by T. So we just want to work out the power. We know there's a potential difference or a voltage across it and a current through it. And therefore we can say that P equals VI, which is just 0.60 joules per second, because that's the same as 0.60 watts. Again, another definition here. This one, and again, there's different ways that you can write this down, but this is just a simple GCSE definition of what we mean by the frequency of a wave. I then sketch the graph here of y equals 3, and between 0 and 3, it's this area we're looking at. So that's just equal to 3 times 3, which is 9. And then the total resistance, what you've got to remember is that the total resistance of resistors in series is you just add them all together. So here that's 1,000, because it's a kilo ohm, plus 400, which is just 1,800 ohms. Fission and fusion, we tend to cover these again in year 13, But this is really about these nuclear events where fission is where you split apart a large unstable nucleus, and fusion is when two lighter nuclei are joined together. Both of these cause the mass to change, and therefore energy is released because some of that mass is transferred or converted into energy. For this one here, y equals 2x, it's just a steeper line, and if we know that x is 4, then y is going to be 8. And now the area is just going to be equal to half the base times the height. Calculate the frequency of a sound wave. Yet again, we've done this many times before, and now you should be thinking that's really easy. A lot of this stuff might seem straightforward, but the more regularly you do it, the more you're going to remember things like the wave speed equation. And you're going to realise that 330 metres per second is roughly the speed of sound in air. Now, I cannot stress how important y equals mx plus c is going to be, especially when you're doing practical work and you might be measuring things, putting it on a graph, and then the gradient and the y-intercept actually mean something. Now, for these ones over here, m is just the number in front of x, so 2, 3, 6, and 3, so don't get caught up by that last one. And the intercept is 3, 2, 3, and 6, straightforward. Rearrange f equals bil sine theta. Now, at GCSE, you might have looked at the force on a current carrying conductor in a magnetic field. Now, that was always, think about Fleming's left-hand rule, everything was at 90 degrees. At A level, we're going to get some of our angles in, and we maybe have the conductor, maybe not at 90 degrees, but we can still work out the force and so on. So to rearrange this is just what I got. And that's why, again, over the previous weeks, I've got loads of right-angle triangles, looking at sine, looking at cos, to get you used to using sine theta if needed. And then we've got the protons, neutrons, and electrons in the following atoms. And if it's an atom, it must have the same number of protons as electrons. But what you'll notice about these is that we've got a couple of different isotopes of iron, and that means they've got a different number of neutrons in the nucleus. And often, when we have heavy things, there are more neutrons than protons. That's going to be really important as we go through the course. For these ones here, in order to work out the gradient and the y-intercept, you first have to rearrange it to make y the subject. And therefore, y is equal to 2x plus 1, so the gradient is 2 and the intercept is 1. And it's the same for this one and this one. And although that's a half x, I've given my answer as 0.5. We tend not to use fractions at A level. Instead, we give our number as a decimal. Rearrange G equals gm over r squared to make r the subject. So this is a gravitational field strength, and that depends on the mass of an object, m, and the radius away, or the distance away from that object squared. So here, r squared equals gm over g, and r is equal to the square root of gm over g. Sometimes you might see a negative symbol, and that negative symbol is really to do with the direction and the fact that this gravitational force is attractive. And also we've got two g's, so capitals and lowercase are really important. Big G is our gravitational constant, small g is a gravitational field strength at that point. This one here, kind of a two-step calculation. We had to work out the resultant force, which in this case was 165 newtons. We had to work out the mass when we were given the weight, and that's 186.03 kilograms. And therefore, F equals ma. A is equal to F over m, which is 0.887 metres per second squared. We're almost there. There's a lot of questions, aren't there? Well done, by the way, on all the work you've done so far. 27th of July, again, I started by rearranging all of these equations. I then used those numbers here and I wrote it out as y equals mx plus c every single time to get our values for gradient and intercept. We've now rearranged this where we're actually looking at the gravitational potential, which equals minus gm over r. I rearranged it to give m equals minus vgr over g. Again, you don't need to know what all of these symbols mean, but you will find that these are going to be more familiar as you go through the course. I suspect a lot of you watching this will have got this wrong because the ray of light is at 25 degrees to the surface of a plane mirror, which just means a flat mirror. Now, if that angle is 25, this angle must be 65. So the angle of incidence is 65. So the angle of reflection, because I is equal to R, is also 65. And that's why I do feel drawing out a diagram can stop you making small little errors in your calculations. 28th of July, the first thing we're going to do is use this data here to work out the gradient, which is our change in y value divided by our change in x value. So that's 10 minus 2 divided by 5 minus 1, which is 2. And then we're going to say that y minus y1 equals mx minus x1. Now for this, I just chose these points over here, so x and y. So y minus 2 is equal to our gradient of 2 multiplied by x minus x1, and that gives y is equal to 2x. For these ones here, we've made p the subject, and actually here, sometimes p represents the momentum, so p, the momentum equals mass times velocity. Other times we use a lowercase p to represent the pressure, and this is the pressure of an ideal gas. This is one of the ideal gas equations. So the pressure is equal to the number of molecules times Boltzmann's constant times the absolute temperature over the volume. Again, you don't need to know what these represent just yet. And here we've got an equation that relates the kinetic energy to the momentum of an object. So P is the square root of 2mEk. Particles, solid liquids and gases, no different really to what you might have done back in Key Stage 3 or Year 7. I'd say what people tend to do is maybe draw these diagrams quite badly. I've tried to show here that the density of the liquid is pretty much the same as the density of the solid, but the density of the gas is about 1,000 times less. Okay, and again, some of this stuff you might look at maybe in Year 12 if you're looking at things like specific heat capacity, but a lot of this is developed more when you look at the particle model of gases going into Year 13. 29th of July, just like we did yesterday, but this time it's actually easier. We know that y minus y1 is equal to mx minus x1. I've got the gradient of 3. I've chosen these values for x1 and y1, and therefore y equals 3x minus 1. Something else which might come up later in the course, potentially if you're looking at some simple harmonic motion and deriving the equation for the simple harmonic motion of a pendulum going side to side, is we approximate sine theta to theta, because when you have a very small angle of theta, that's approximately equal to sine theta. Small angles of theta mean that cos theta is about 1, and tan theta is sine theta, which is theta. Okay, again, if you're doing maths, you're going to love this stuff, and later on this could become quite important. We've now got just trying to find the height that something rolls down. Again, assuming there's no friction or anything like that, we're going to equate the potential energy to mg delta h, rearrange this to make h the subject or the change in height, and that's equal to 30 meters to two significant figures. Just a couple more days to go now, so we're getting towards the end of that first month. So these ones here, I just did a sketch, straight line graphs, because it's the y equals mx plus c, and I just put in the intercept as 1 or 3. Half-life, a couple of ways we can define it. We can either think about the number of radioactive nuclei, which is n, or we can think about the amount of radioactive decays per second, which is the activity. And again, these ones here, two ways of defining radioactive half-life, which again is something we tend to look at a little bit more when we look at nuclear physics towards the end of A-level physics. This one here, we could have written down SUVAT, but I'm going to use the equation A equals V minus U over T. I'm going to put the numbers in to find that here, again, when it slows down, it's going to be a negative acceleration or a deceleration of 2.8 meters per second squared. And the final day, is anybody watching this video? If you are, I really hope that this has been useful to you. 31st of July, sketch the graph of y equals e to the x and y equals e to the minus x. These are exponential graphs which you need to understand as you go into the second year of A-level physics. At the moment though, if you don't know what they look like, you can easily Google it and just put your sketches on here. Electrical resistance is really just the ratio of the potential difference across a component to the current through it. So R equals V over I. And finally, we've got some nuclear equations. We're going to start with uranium. Now, if it's giving out He, And sometimes we use an alpha symbol, 2, 4. That shows it's got 2 protons and 2 neutrons inside it. We know that numbers therefore must be 2 and 4. And the total amount of protons at the end, 90 and 2, is going to be the same as the total number of protons at the beginning. And just like we had 238 nucleons, 4 have been emitted, leaving 234. Now this thorium then gives out beta minus radiation, and this is because a neutron turns into a proton and an electron. So 91 minus 1 is equal to 90, and the numbers at the top add up as well. And this then emits another beta minus, and it goes from 91, because this number here must be the same as this number here, because it's the same element. And if we've got minus 1 here, that must be 92. And if it's 92, then it must be uranium, in this case 234. So we've got a bit of a chain here, where we have alpha, then beta, and as it does so, it means we end up with uranium, but a different isotope, and potentially a little bit more stable. So those were the answers for July for book 1. Hopefully that makes sense. What you can now do is pat yourself on the back. You've done amazingly well. And maybe just have a look at the July review and just fill this in with where you think you are at the moment. Can you use Pythagoras? Can you identify the opposite, adjacent and hypotenuse sides of a right angled triangle? Can you rearrange simple equations? Anything else you're maybe not sure about, you can add some comments there. And as you've kept track of your progress, if there's any questions you haven't done so far, you can always go back and review them at the end of the month. So that is a daily workout, and they're the answers for July.